Okay, back again. Chemistry 3202, course overview, Unit 1, Section 2 now, Lesson 1, Equilibrium. Equilibrium may be considered to be a balancing act, so I can't resist. Got to hum the theme to Mission Impossible, right? Do 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 do. Anyways, the textbook's readings for equilibrium here listed below, and some items that relate to this. And again, make sure you take advantage of the content that's on the D2L page, as well as the government website for all public exams and things like that. And don't forget, you should be taking advantage of our online tutoring. Here we go. Here's what we expect you guys to know from this section. Dynamic equilibrium, simply put, is a process where we have two opposing forces happening at the same time. All right, good versus evil, day versus night. Everything's happening at the same time. So two opposing forces happening at the same time. Now you guys have already been experienced with a little bit of dynamic equilibrium because we looked at the situation where we had a dynamic equilibrium where we had saturated solutions, where we said the rate of dissolving equals the rate of crystallization. So here's the two opposing forces. You have dissolving, where the crystals are being pulled apart and being pulled into the solution, and then crystallizing, where the particles would collide again and stick together and fall to the bottom as a solid, so they would recrystallize. And we said that was going on at the same time. And we knew that was an example of a saturated solution. In this particular example, we're seeing that sodium chloride can dissolve, in which case it's going to dissociate and move out into the water. So this is the dissolving or dissociation process for the ionic compound. But at the same time, if the solution's already crowded with sodium ions and chloride ions, that this guy really wants to break apart and come out into solution. But as soon as so many sodium ions get pushed out, it's already overcrowded. So what happens is other sodium ions and chloride ions begin to stick together and stick onto the crystal and recrystallize. So the shape of this crystal begins to change. That's our observation. The amount of solid sodium at the bottom, or solid sodium chloride, doesn't change, but it changes its overall shape. It begins to sloop down and starts changing over time. But the overall amount of the material stays the same. So we can say that the rate of dissolving is equal to the rate of crystallization. If 10 sodium chloride molecules should happen to break down, then that's going to squeeze out 10 more and say, hey boys, there's no room out here, we're already full. So what has to happen is a set of 10 has to fall out of the solution, and this is going to be a continually never-ending process, and that's what we refer to as dynamic. Dynamic means constantly moving, constantly changing. Equilibrium, state of balance. Okay, so that's what we're looking at here. Now we want to relate this to chemical reactions. We want to look at a chemical reaction where we actually have bonds breaking and bonds reforming. So in this case, we're saying a chemical equilibrium is achieved when the rate of forward reaction equals the rate of reverse reaction. Now, the important word here, of course, is we've got forward being equal to the reverse rate. So there's your opposites happening, right? Forward is opposite to reverse. Now, the important thing here that you have to keep in mind is that it's the rates that are equal. And that's going to be a common theme throughout what we're going to talk about. It's the rates that are equal, not the concentrations, not the number of atoms, but it's the rate at which the forward reaction proceeds, which is equal to the rate at which the reverse reaction breaks down. Okay, so in a sense, we see this as being this dynamic in that it's like a seesaw. It's always shifting back and forth, never stopping, forward to reverse, reverse to forward, forward to reverse, and it continues and continues. Here's a typical chemical reaction that we can look at. We can have a chemical reaction where we can have hydrogen reacting with iodine, producing 2 hydrogen iodide, and energy is going to be released in the process. Now this is just like the sodium chloride situation, where if 10 molecules decide they're going to collide and chemically react, providing they have sufficient energy and they have correct orientation. Then if 10 of these molecules move forward, then what's going to happen is, for some reason, on that side, everything is overcrowded, and that's going to cause 10 hydrogen iodides to say, boys, well, there's not enough room over here for us, so what we have to do, of course, is break down and go back the other way. So if 10 are let in, that means 10 have to be pushed back the other way to make room for the ones that just came. So we want to keep this forward and reverse rate the same because everything is blocked up. All right, now we can look at this and say, all right, let's take a flask here, and I'm going to black this out and say, okay, we don't have any hydrogen iodide in the flask yet. Okay, we haven't started the chemical reaction. And we're looking at this and we're saying, all right, iodine has a distinctive orange color. You guys have cut your fingers and your mama put iodine on to try and kill the bacteria and whatnot and help you heal and all that stuff, right? It's orange. It causes your skin to go brownish orange. So if we put hydrogen and iodine in that flask, it's going to be a really dark orange color, all right? And if we could somehow magically say, boys, don't react yet, not yet, not yet. We're not going to start up yet. All right, it stays orange. As soon as we start the chemical reaction, what happens is the reaction begins to flood in the forward direction. Right? Instantly the reaction pushes forward because these guys are colliding, and as soon as we open up the gates and say, let her go, boys, that these two begin to collide and chemically react. And now what's going to happen is as this pushes forward, the orange color is going to start to fade. Because what's happening in this container is we're starting to produce some hydrogen iodide. Some of the iodine is starting to disappear. However, as this reaction pushes forward, the hydrogen iodide starts to build up. And as the hydrogen iodide starts to fill up this container, eventually is going to come a point where the conditions are not going to favor hydrogen iodide. And as the hydrogen and iodine start colliding to produce HI, these guys begin to break down. So at first you're going to see a really orange color and the orange begins to fade. But after a while, as we start circulating back and around, what you're going to start noticing is that if 10 iodines break down to produce HI, that gets rid of 10 atoms that are causing orange. What happens is, at the same time, 10 more molecules that make orange are going to reappear. So after a short period of time, the orange color is going to stay constant because as they break down, more are forming. So we see that that equilibrium, the rate of forward is going to equal the reverse of the rate reverse. So the amount of orange intensity will be constant at equilibrium. And the reason for that is because the amount or concentration of iodine is going to be constant because if 10 break down, 10 more come back to replace it. So it's or 100 or 1,000,000 or whatever, right? 1,000,000 go forward, 1,000,000 come back, or large numbers. But whatever it is, it's the rate forward is going to equal the rate in reverse. And because of that, the iodine concentrations are going to be held constant. And what we're going to see is that the orange color, look at that spelling of orange. That's orange. Orange. There we go. The orange color, I'll fix it for you, remains constant, and this is a visual cue that says, hey, if 10 molecules break down and 10 return, then we don't see anything happening, but we know it's happening because it's a dynamic equilibrium. Okay? So that's what's going on here in dynamic equilibrium. So some of the conditions that we need for an equilibrium to occur, there's 3 of them. Number 1, it has to be occurring in a closed system. Nothing can get in, nothing can get out. Let's go back and look at it. The main condition, if you've noticed, is that there was a rubber stopper in this flask. If hydrogen iodide was allowed to escape here and go out through the bottle, then the reaction would never get backed up. The hydrogen iodide would never ever have to collide with other hydrogen iodides because it would have escaped from the bottle. This whole process is based on the idea that as this reaction moves forward, this stuff begins to build up and begins colliding with other hydrogen iodide molecules, in which case the bonds begin to break. So that rubber stopper there is so very, very important when we're dealing with gases because we don't want those gases to escape. If it does, it's going to upset the balance, and it will never get a chance to back up, so to speak. Okay? So we need a closed system. So closed to the flow of matter. So the matter not allowed to leave or enter, but energy can get in, right? We can warm this up or cool it down because it's only a glass bottle after all. You know, if the temperature of the room changes, then that energy change is going to be felt inside the bottle as well as outside, right? So the only thing that matters here is if matter doesn't get, see, the only thing that matters is matter, right? So as long as that doesn't get in or get out, then it should be able to back up. So nothing can enter, nothing can leave. It needs to be capped off in the case of gases. Okay, if it's an aqueous solution, then of course it should still be capped, I guess, so that the water won't evaporate from the aqueous solution. But you know, you still see the equilibrium a little better in the aqueous solution because it's not going to be a rapid evaporation of the gas, or sorry, of the water. But for gases, it's very important that you cap it off, especially. Okay, number 2 here, the macroscopic properties must appear to be constant. Now remember when we looked at that one, we looked at the orange color. At first the orange color faded a little bit, but if we left it long enough, what happened is it got to a constant level. Because if 10 iodines or 100 iodines were removed by going forward, then 100 had to be replaced to come back, right? So the level of the iodine was being constant, and that's what was causing the color change. And other things that we can look at that have to be constant would be the temperature. You know, if a chemical reaction was endothermic or exothermic here, as this reaction goes forward, it's producing heat. The more it goes forward, the more energy or hotter it's going to get. But what we need to say is that if this temperature is going up, then the reaction is moving forward. If the temperature is going down, then the reaction is going in reverse. But because this reaction goes forward 10 times per second, and at the same time it's coming back at 10 times per second, any energy that's being produced in the forward reaction is instantly being consumed when it goes backwards. So the net effect of the energy is it cancels one another out. So we don't see a temperature change. That should be constant. Okay? Pressure. If we look at these guys, we've got gases being produced here, and the amount of gas that's in this container is going to be the same no matter what. You either have hydrogen iodide gas here, or you've got hydrogen and iodine as a gas. So the gas pressure should stay constant. Whether we had more moles on one side or another, that's another issue that we're going to talk about. But in any case, the gas pressure should not change, which would indicate that nothing extra is being produced. So if anything's being produced, it's instantly being consumed again. So these things have to make it look like nothing's going on. All right, and the macroscopic properties are the things that we can detect and measure with our senses quite easily. And number 3, the reaction has to be reversible. The only way we can get something to go backwards is if it's a reversible reaction. So we like to represent reversible reactions using these double arrows to indicate forward and reverse. We don't like to do this, all right? Sometimes you might see that. You might even see me do this from time to time, but we don't accept that. We really like to have these double arrows like that. And no way do we like that. That's a super no-no there, right? So double arrows like this. And this is a situation where we got our double arrows and we're showing you how solid water is being melted to produce liquid water, and we all know that that's a reversible process. Solid water, you add heat, it melts. Liquid water, you remove heat, it freezes, all right? And we can always get liquid water and solid ice depending on whether we add or remove heat. Put that in an open container and it evaporates, it disappears, but we need this in a closed container so the liquid water will not evaporate. Okay, there we go. Some of the things that we can look at then that must not change over time: color intensity, obviously, just like with the iodine. The amount of solid material at the bottom of a reaction vessel, like the sodium chloride, right? The crystallization, the dissolving process. If it's the same rate, then the amount of solid should stay the same. If 10 dissolve, then 10 have to crystallize to take their place. The pressure of the system, all right? If you have any gases being produced, if we continually produce those gases, then the pressure will build up. But we won't have that happening at equilibrium, because 15 molecules of gas are produced, then that means 15 more molecules have to break down to keep everything constant, right? The rates have to be the same. The temperature, we've already talked about that one. And finally, the reaction of the volume of the reaction solution. If we're dealing with a liquid that's being produced or consumed, you know, if more liquid is being produced and the liquid level starts to rise, that means we're not at equilibrium. Because if 20 molecules of liquid are produced, then 20 more should be taken out of the solution to compensate. So everything should be constant. These things should not change. Okay, here's a graphical analysis of what's going on here. So I'm going to black out a few things here just to draw your attention to what's going on here. Okay, if I black out this particular graph here, we're looking at this from a graphical nature, and what we're going to be graphing here is the concentration of each of these reactants and products versus the time that they're going to be in the bottle. Now, if I look at my reaction container and I say, okay, in the very beginning here, in this reaction bottle down below, I'm going to put 2 moles of hydrogen and 1 mole per liter, assuming this is a 1 liter container, we're going to put 2 moles per liter hydrogen and 1 mole of carbon monoxide. So we're going to put that in our flasks here. Now, as this reaction pushes forward, we're looking at this chemical reaction. As the reaction pushes forward, what's going to happen here is the hydrogen values are going to start to drop. And what we're going to see is a graph that looks something like this. The hydrogen levels begin to drop because the reaction's going forward, hydrogen is being consumed. At the same time going forward, the carbon monoxide levels begin to drop because it's also being consumed. If we look at the methanol, the CH3OH, as this reaction pushes forward, the methanol starts at 0, but it begins to build up because more and more methanol is being produced. So as these guys are being consumed, the concentration of these guys go down, this guy begins to go up. Okay? Eventually we reach a point where as the concentration of methanol begins to build in this closed container, what's going to happen is the methanols begin to collide with other methanols. And they start reacting with each other and breaking down. So at that point, when the concentrations get to the point where the methanols begin to collide with one another, and if 10 methanols are produced or 20 methanols are produced, then they would collide and they would instantly break down to produce the carbon monoxide and hydrogen. So this reaction begins to reverse itself. Now you will not see a drop in the concentration of methanol because what's happening now is as the methanol is produced, the same amount that's produced is going to be the same amount that's broken down. So that's why the concentration doesn't change. And likewise over here, we start dropping the hydrogen concentrations to a point, at which point if more hydrogens break down, they're instantly being replaced by the breakdown of methanol. So what happens is the concentration stays level. Same thing is true for carbon monoxide. It begins to drop, and then eventually what happens is if 25 molecules of carbon monoxide break down, then at that point 25 more come back to take its place. So the levels of carbon monoxide don't change, and that's what we see going on here. So if we do a further analysis here, this is where the forward rate is going to be the fastest. And the reason the forward rate is the fastest rate here is because this is where the concentration is the highest. So the reactants are at their highest concentration. This is where we're going to get most collisions. So the forward rate is going to be fastest here. Okay. The forward rate begins to slow. The reason why the forward rate begins to slow is because the concentration is beginning to drop. Fewer collisions. Eventually, the concentration drops to the point where that's where it will be its slowest, because that's where the hydrogen is at its lowest concentration. That's where it has the fewest collisions. So if we were going to analyze this for the rates of reactions, the forward rate is fastest here, slows down, and this is where it would be at its slowest point. It hasn't stopped, right? Because equilibrium would say that it has to keep going. This is where it would be slowest. If we analyze the other graph and say, okay, let's start from here where we have nothing, we don't have any collisions between the methanols here. So as we start building up the methanol, we're starting to get a few collisions, but not enough, is it? The reverse rate is going to be very slow from the beginning because that's where the concentrations are the lowest for the reverse reaction. As we begin to proceed with the reaction, the levels of methanol begin to increase. More collisions. So what's happening now is the reverse rate is beginning to pick up. You see what's happening here? The forward rate was fast in the beginning, the reverse rate was slow. The forward rate begins to slow down where the reverse rate begins to pick up. And eventually we get to a point where the methanol, the reverse rate is going to be the fastest because this is where the concentration of methanol is the largest. We got the most collisions. So it's like a reverse thing happening here. At this point though, the forward rate is equal to the reverse rate. And there we go. So once the equilibrium is reached, the concentration of the reactants and products becomes stable. We know that because we won't see any color changes. We won't see any changes in pressure. There's no changes in temperature. Everything becomes constant and stable. All right, so the number of collisions becomes stable. And what happens is the collisions don't stop, do they? There's collisions happening, and if there's collisions happening, then therefore there's reactions happening. But what's happening is the rate of the forward collisions that are successful are equal to the rate of reverse collisions that are successful, and we're now in a state of equilibrium. Okay? Now what we want to do is merge these two graphs to see what they're doing together. Okay, and what we see happening here is as the hydrogen and carbon monoxide drop, the methanol begins to go up. And you notice how they're becoming stable around the same place, aren't they? So we're going to draw a little line here, and we're going to say at that particular vertical line, that's the point where equilibrium is attained. That's the point where the concentrations become stable. Okay, and there we go. So we can indicate on a graph anywhere where equilibrium is attained because that's where the concentrations level off. Does the reaction stop? What it's saying is that the amount of methanol that breaks down to go reverse is simply going to be replaced by the same amount of hydrogen and carbon monoxide that come forward. So everything becomes stable. If any one of these was causing a color change, then obviously they're not going up or down, so the color change would be constant. Everything would be held constant here. Here's another example. All right, this is like a public exam type question. It's saying consider this equilibrium. And it says assume that nitrogen and hydrogen have been placed in a closed flask. Right, there we go, so it can't escape. And they react to produce ammonia. Describe the changes in the concentration of each species from time 0 to the point where equilibrium becomes stable. And what we see here is that the hydrogen and nitrogen are going to drop. And at some point in time, they're going to become stable. The hydrogen begins to drop as well, kind of at the same rate. And then that levels off and becomes stable. And at the same time then, the nitrogen levels would drop. Now, some people would say, well, do they have to intersect? Do these lines have to intersect? Could I draw nitrogen intersecting and then leveling off up top like that? Or would it be acceptable to draw nitrogen here and level off underneath? Well, we'll study that later on in another lesson where we look at how far the equilibrium is going to go, right? The position of equilibrium. You know, if you're on a seesaw, if you're heavier than the buddy you're on the seesaw with, then you're going to be sticking him up in the air. If he's heavier than you, then he's going to be popping you up in the air. So the relative position of where the equilibrium is, in this case, you know, how much ammonia are we going to get, is going to depend on a few factors. So whether you intersect the lines, like I have in the top one, or whether you don't intersect the lines, at this stage it really doesn't matter because we need to do some calculations to figure that out. So I'm going to leave it like that. And what you would do here now is simply draw a vertical line which would indicate that everything is leveled off here now, and the reaction does not stop. The forward rate is equal to the reverse rate. Okay? And there we go. If we wanted to do a little analysis here, hydrogen starts at its highest, and then it gets consumed a long way until it starts to drop, and then we reach equilibrium. And ammonia starts at 0, and the concentration begins to build until it becomes stable when we've reached equilibrium. Okay, here's a few questions that you might see on this. It says, in a system at equilibrium, what can be said about the concentration of the reactants and products? The concentration, they don't have to be equal, and you can go back to the charts. Look, these guys are not equal. There's different amounts of ammonia, different amounts of hydrogen, different amounts of nitrogen. They're not equal. What is happening is they're stable, they're constant. They don't fluctuate around an average. And they're not random, all right? There is a method to what we're doing. They're constant. Where they end up being, again, in another lesson, we're going to determine that and say, well, where is going to be that stable position? We're going to look at that later. So we're saying that the concentrations at equilibrium will rarely, if ever, be equal. They will be stable. Only stable. Okay? The only thing that's equal in equilibrium, I can't stress that enough, I said it at the beginning, the only thing that's equal in equilibrium are the rates. That's very important. Okay, we can put a little footnote there if you want. There you go, a little footnote, 4-toe foot. There we go. Okay, number 2, which statement describes the conditions in any equilibrium, any system at equilibrium? And the answer to that, of course, is the reaction rates stop? No way. It never stops. It's continually going. The mass of each chemical species remains constant. Could be. Right? The moles of the reactants equals the moles of the products? No, because the only thing that's equal is the rates. The temperature of the system fluctuates or changes? No, it's got to be constant. So the answer to this is B. It looks like the amount of material stays the same. Number 3 here, which of the following is an example of dynamic equilibrium? Dynamic means it must be moving or changing. Equilibrium means it must be opposite forces. Okay, so it must be opposites that are we seeing here. Okay. If we look at each of these guys, we say a closed flask. Okay, that's good. It's a closed flask. It's half filled with water. There's an air space over it, and it's left for a long period of time. Okay, well, let me graphically show you what's going on here. We've got a closed container. We've got some water in here. We've got some air space. Over time, what's going to happen is the water is going to evaporate to produce gaseous water. The gaseous water is going to collide with the sides of the container and condense to form a liquid. And so the process goes, all right? Evaporation, condensation, evaporation, condensation. That sounds good to me. In B, it says an ice cube in water at 10 degrees Celsius. Well, at 10 degrees Celsius, the ice is going to all melt. It's not going to freeze up anymore. So that's no good. You only have one direction. An open flask containing potassium metal? No. The potassium metal is actually going to react with the water vapor that's in the air and disappear. It's going to be gone forever. And D, dissolved salt in an unsaturated solution? Absolutely not. The only type of solution that's equilibrium is saturated. All right, so the answer is A. And number 4 here, which statement is true when the reaction reaches equilibrium? And we're saying here that all the nitrogen has been consumed? Absolutely not. If it was, then the reaction would never be reversed. We have to be able to have some of everything present in order for the reaction to go forward and reverse. No nitrogen N2O reacts to form N2 and O2. That's not true. If it was going to be equilibrium, then it has to be, some of it's going to break down, right? It's got to be give and take. Pressure changes no longer occur. That's good. Pressure is constant. And the answer to that is C. And that's definitely not right. Okay, there we go. So that's equilibrium. Don't forget to take advantage of our online tutors and the online content. Don't forget there's old public exam reviews there. We go over them question by question. Check it out. Bye-bye.